our last example before we close our discussion in Faraday's law in this chapter. This is also from the textbook, but it's a little different from the real problems that we did before. This time there is a real battery. Okay, there's a real battery, and then look at the structure here. This is two long parallel wires, two parallel rails, and here is a complete loop, complete with a movable metal bar of length d. Okay, of length d. There is a uniform magnetic field penetrating into the paper. Initially, the bar is not moving. Okay, it is not moving, but there is an EMF which powers a current, and that current, of course, runs like that, right, in the loop. So it runs like that. There's a current. Now, you can easily find the direction of that current, which is like that, and as a result, the direction of the magnetic force exerted by this magnetic field on that current, I, L cross B. L follows the direction of the current, L cross B. So L goes this way, B goes in, so L cross B would be pointing this way. So it's going to be moving in this direction because there's a magnetic force pulling it this way. Okay, there's a magnetic force pulling it this way. But as it moves, it's going to begin to cut into magnetic field lines, right? And as it cuts through the magnetic field lines, it will generate an induced EMF. And that induced EMF will change the net EMF of the entire loop. Do you agree? Okay? And as a result, the current will change. Because the current is epsilon over R, assuming this bar also has a resistance of R and nothing else has a resistance. Okay? So as the net EMF changes, the current I is also going to change. Okay, so what I want to know is what? What I want to know is how is the speed going to change for this bar as a function of time? Okay, let's first take a qualitative look at how the speed is going to change. If we do not consider the effect of Faraday's law, in other words, due to the bar cutting through over the magnetic field lines, producing an increased EMF, induced EMF, then the problem is actually pretty simple, because you have a stable current I going through it, and that stable current I will be subject to a stable uniform magnetic force, which is IBL. L is actually equal to D in this case. So you have a uniform acceleration because the force is uniform. So the force would then, the speed would then increase linearly as a function of time, because it would be uniformly accelerated motion would be like this, right? Straight line. Okay, now we have to consider Faraday's law, of course. As the bar moves this way under the influence of the magnetic force, it is cutting through magnetic field lines and therefore generating an induced EMF. We can take a look at the direction of the induced EMF. Okay, you see, as the bar moves this way, it is going to decrease the magnetic flux through this enclosed space, enclosed region, and so there is a decreasing flux. Okay, and the Faraday's law says that then the induced EMF is going to try to stop this from happening, so that it would promote an inward magnetic flux, and that can be done with only with a current flowing like this, right? Because the current flowing like this will produce an inward magnetic flux or magnetic field, and that means that the EMF, the induced EMF, drives a current that is opposite to the existing current. So effectively speaking, this is like a positive terminal of a battery, this is like a negative terminal of a battery. This EMF opposes the original EMF. Okay, so the net EMF would be the original one, epsilon, minus the induced EMF, epsilon induced. That is the net EMF which drives the current I times the effective resistance R carried by the bar. Now, initially, the induced EMF is very small because, after all, it is proportional to the speed of cutting. Initially, that speed is 0. In fact, even it grows, it still starts with a very small value. So epsilon is much greater than epsilon induced, and you have a rather large current, which means there is a rather large acceleration. Okay, but gradually, as time progresses, the speed is going to go higher and higher. That makes the induced epsilon greater and greater this original epsilon cannot change, so the net EMF goes down, and the current goes down. As the current goes down, the magnetic force also goes down because it's proportional to the current. So that means the acceleration is going to get smaller and smaller. So it's going to fall off that straight line. Okay, the speed is not going to keep on increasing linearly. As a matter of fact, at some speed, the bar is moving so fast, it is cutting through the field line so fast that it is generating an induced EMF which exactly matches the original EMF, except is in the opposite direction. In other words, at that point, epsilon induced equals epsilon, and then the net epsilon is 0, the current is 0, the magnetic force becomes 0, and then what happens? There is no acceleration. Okay, you have reached the final saturated value, the final value of the speed, which we call V maximum. Okay, so the actual speed should increase like that. Right? Should increase like that. Now we are veterans at this type of problems now. We know how to find V maximum, for example. Okay, V maximum is reached when there is no current. In other words, there is no magnetic force, so the acceleration will be 0. And so we basically set epsilon to be equal to epsilon induced in order to find V maximum. Okay, epsilon induced is B L V. L is D in our case. B D V. V is V maximum. Okay, so this tells us that V maximum equals to epsilon over BD. Before we do any serious calculation, we already know what kind of final speed is going to reach. Alright, but how does one find the entire curve? Well, to do so, we must solve for the equation of motion. The equation of motion is F equals ma. F, there's only one force on it. It's the magnetic force. Okay, so F equals Fb, and that equals ma. And the magnetic force is B times I times D, the length of the bar. And then in order to solve this problem, I have to know what the current is, which I get from the top formula here. So I is equal to epsilon minus epsilon induced divided by R, so I'll plug that in. B times D times I, which is epsilon minus epsilon induced over R. And that epsilon induced is BdVm. Okay, actually BdV in general. BdV. Okay, and the other side is mass times acceleration, mdv/dt. Now, this is a differential equation for V. V is the unknown function that we wish to solve. Okay, how do we solve this type of problem? Well, we did a couple of earlier examples, and we have a pretty good idea how to do that. In fact, there are 3 terms if you work this equation out. If I break these 2 terms, the first one is B d epsilon over R, and then the next term is minus B squared d squared over R times V, and the other side is m dv/dt. Now it is clear that except for this constant term, you got 2 terms here. One is V, one is dv/dt, and to make this equation valid for all the moment t, all values of t, you have to make sure that V and dv/dt should have the same type of functional dependency. That's how their time dependency will cancel out, leaving only a constant on that side. Okay, so again, V should behave like some sort of exponential function, because that's the only function that will retain the same functional form, and you take the derivative. So and we know specifically it should go up like that. So we're pretty good at this, right? We know that ansat or the trial solution should look like this: V as a function of time, V maximum 1 minus e to the negative alpha t, right? This is something we've done a couple of times before. Now we can find V maximum and we can find alpha. The way we do that is to plug this into here. Okay, we plug this into here. See what kind of function, what kind of equation we're going to get. Okay, so we can copy this term here. We can copy this b d epsilon over r, then minus b squared d squared over r, and then v, which is right here, v maximum 1 minus e to the negative alpha t. Now the other side, mass times acceleration, m dv/dt, so you take a derivative. Okay, take a derivative, which is alpha v maximum e to the negative alpha t. Okay, what do we do now? As we did before, yeah, we move all the time-dependent term to one side. Actually, there are only 2 time-dependent terms. One is here, one is there. I'm going to move it both to, say, the right-hand side. So the left-hand side, you have what you have left are these two terms, these two constant terms. So the first one is b d epsilon over r. The next one is b squared d squared over r, and then v maximum. Okay, that's what you have left on the left-hand side. These are all constants. Now the right-hand side equals to, I'm going to take that e to the negative alpha t out, e to the negative alpha t out. There's a v maximum, common term which I'm going to take out. What's left is m alpha. Okay, m alpha here. And what's left there, negative signs cancel out, minus what? You took Vm out already, minus what? B squared, D squared over R. Alright? Now, the next step is routine, something we did before. Remember the argument? This is the only time-dependent term, and yet, as time changes, you want these two sides to be always equal to each other, regardless of what t is. And that is impossible, because the left-hand side is a constant, right-hand side changes, unless you make this equal to 0, and you make this equal to 0 correspondingly, right? And then that gives us an expression, two equations, one for this, one from this, one from that, and from these two equations we can see, for example, from here we can solve for V maximum. Okay, so from this equal to 0, we found V maximum to be equal to what? This over that, b d epsilon over r divided by b squared d squared over r. So what do we have? It is equal to epsilon over b d, right? And you see, that agrees with what we got there. See that? V maximum. So whether we got it directly from Newton's second law, physical intuition, or we get it by solving the differential equation, we get the same result. Okay, and the second one is to find alpha. Then you get it from this formula. Okay, you set this equation to be, this side to be 0, so you get alpha equal to what? B squared d squared over m over r. That is alpha. Okay, so the complete solution, the speed v as a function of time, you know it looks like this, right? It looks like this, but the complete solution, I can write it down now. V as a function of time for the bar is V maximum, which is epsilon over b d, 1 minus e to the negative alpha t, so it's b squared d squared over mr times t. Okay, this is the complete expression for the speed of the bar as a function of time. Now, when we can take a look, at this result and see if it makes sense. The parameters involved are epsilon, b, d, m, and r. Okay, those are the 5 parameters involved in this problem, and we can take a look at how these parameters will affect our answer. First of all, the final speed. Okay, you know, without any inference from Faraday's law, without induced EMF, there is no limit to the final speed. It's going to go to infinity, right? In theory, it's going to go to infinity. And the reason why you have a limit is because of Faraday's law. And look at the final limited value of V maximum, what you get. Epsilon over B over D. Now, suppose you have smaller d, so you have a smaller bar cutting through the magnetic field lines, and you have a smaller magnetic field. Of course, that is going to reduce the effect of Faraday's law, right? Because you're using a smaller bar cutting through a weaker magnetic field line, and therefore you will not have as much effect from Faraday's law, so the speed can reach higher value. And also proportional to epsilon, because a greater epsilon, greater EMF promotes a greater current, which can cause greater magnetic field, magnetic force if everything else is the same, and therefore pushing you to a greater final speed. So this makes sense. Okay, this makes sense. Now on that side, look at alpha. Alpha equals b squared d squared over mr. Now mathematically, the greater the alpha is, the faster it's going to reach a saturated value. Okay. Now the reason why it reaches a saturated value, once again, is because of Faraday's law. Okay. So let's see. If Faraday's law is relatively important, okay, then it's going to reach the saturated value greater, which means alpha will be a greater number. Now, that happens, of course, if you use a longer bar cutting through a greater magnetic field, right? Then the cutting would be more effective, and indeed, when B is greater and D is greater, alpha is greater, so you reach the saturated value faster, which means Faraday's law plays a greater role in this problem. And what about M and R? Well, M is the mass of the bar. It doesn't care about Faraday's law. If everything else is the same, but it's a very massive bar, then of course Faraday's law has less of an effect, because being more massive, it has more inertia. It want to keep on going. Okay, so that will take. It means it's going to take a longer time for it to reach the final speed, right? And what about R? Well, if everything else is the same, a smaller resistance, what does that mean? It means it's going to get you a greater current, right? If everything epsilon is the same, for example. A greater current means greater magnetic force, which means greater acceleration. So with greater acceleration, of course, and the same final V maximum to reach, to access, with a greater acceleration means it's going to reach there sooner. So therefore, it's going to make alpha greater. That's what a small r means. So you see all these parameters, we can understand how, at least qualitatively, how they can affect the value of alpha at the time to reach maximum. So this is yet another example of Faraday's law in action. And please make sure that you understand not only how we solve the differential equation, which is based on Newton's second law, of course, but also the qualitative feature of the solution, and make sure you understand how the speed depends on those parameters qualitatively, epsilon b, d, m, and r. Only a qualitative understanding can make you more comfortable with this type of problem. Only have the mathematical solution, you don't know where it came from, then you don't really understand the problem. Okay, so make sure you always make a qualitative analysis, how these parameters depend on what will affect the answer. Okay, another issue I want to discuss with you is the energy aspect of this problem. From conservation of energy point of view, as the current is powered through the battery has to do work, and the power delivered by that battery is always I times epsilon, right? I times epsilon. And one wonders, where did that energy go? Okay, the power expended by battery is like this. Where does it go? Okay, so energy consideration. Well, this power delivered by the battery has to go somewhere, and it goes two ways. Okay. In other words, the effect of this power. One is, of course, some heat has been generated, right? Because there's a current going through a resistor. So that power is I squared times R, right? What else? Well, the other thing is that there is a magnetic force pulling the bar, so that increases the kinetic energy of the bar. The rate at which kinetic energy increases is dk dt. So, if energy consideration is correct, then you should have this identity. The power delivered by the battery, part of it goes to the thermal dissipation, thermal power dissipated on the resistor, and another part becomes the rate of change of the kinetic energy of the bar. Okay, the question is that right? Okay, I want to see if this is right. Well, let's see how we can do that. Well, first of all, we understand Newton's second law works for this problem, right? We've done this. And Newton's second law says the magnetic force equals mass times acceleration for the bar. So that is B VD. Okay, actually, that's, no, not BVD, BIL. Okay, please do not confuse that. I got confused too sometimes. BVD is epsilon, okay, it's the induced EMF. BIL is the force, all right, is the magnetic force. It's BIL, L here is D, so BID is the magnetic force, and that equals mass times acceleration, so it's M dV dt. Okay, now, what I want to do is I want to multiply both sides by V, okay, both sides by V. So there's V here, and there's V here. And tell me, what is this equal to? V dV dt, isn't that d of 1/2 V squared? Now you stick that m in, isn't that d dt of 1/2 mv squared, right? It's the same, if you work this derivative out, m is a constant, 1/2 v squared, you take derivative, isn't that v times dv dt? Okay, so that's just dk dt, right? This side is just dk dt. Now, take a look at this side. It's bi dv. Can we somehow simplify this? Well, what is BVD anyway? BVD, okay, isn't that the induced EMF? Okay, because it's actually its motional EMF as a cut through diagonal field lines. The induced EMF or motional EMF, isn't that B times V, the speed of cutting, times the length of the bar, which is L? So I can write this BVD as epsilon induced. Epsilon induced times I equals to dk dt. Okay, so dk dt can be replaced with epsilon induced times the current. Okay, now can you see if this formula is valid? Can you see if this formula is valid? This is epsilon induced times I. Here is epsilon times I. Alright, so let me combine these two terms. Okay, so I have I epsilon minus dk dt. I'm moving this dk dt to that side and replace dk dt with epsilon induced times I. Okay, is I epsilon minus I epsilon induced. I can do that, of course, because this is equal to that. I can see from here, right? Isn't that equal to I times epsilon minus epsilon induced? But wait a minute, what is epsilon times epsilon induced minus epsilon? Isn't that the net EMF of the loop? And what is that equal to? I times R, right? That's Kirchhoff's rule. So this is I times R. So it's I squared times R. See? Okay, now move this term back. Okay, move this dk dt back to the right hand side. I get I epsilon equals to I squared R plus dk dt. See that? This is absolutely right. Okay, this is absolutely right. See, this, you can now remove the question mark. We know it is right. So our analysis proves explicitly that energy is indeed conserved. Or we can say our previous analysis based on force, the magnetic force and Kirchhoff's rule, they are in agreement with the conservation of energy, which of course has to be the case.